Man, more missed quizzes.
Really not good day.
So it's not a good day.
Yeah, I was crying down the street while driving.
You did get it back, or are you getting it back?
Oh, no, the grade was on the blackboard this morning. Yeah, I was driving down the street and like real shocking. Like,
Was it bad?
Yes.
Like what was this like a normal 370 test?
Yeah.
They were crappy.
Well, I thought I did okay, but the grade was not okay. Yeah.
So you thought you did better than you earned on the test.
Yes.
At least I missed all the pine cones on the way here.
You missed all the pine cones.
Oh.
Oh.
I got real sad this morning.
So you were crying?
Yo, I was stopping at the red light looking at my grade.
Like over and over again to making sure you didn't see the number wrong?
Yes. I'm real shocking.
Is that a W?
Wumbo.
Oh my god.
You tried.
But
look at that.
All right.
And my shoes get wet, and then I got here late, and I missed a quiz. What the heck?
I could really find more for his test right now.
All right, you want me to make you feel better?
What?
You didn't actually miss a quiz.
Oh, what
These
is
were her notes. We were screwing with you.
Yeah, these are all my notes.
I've taken pity on you. All right, so today.
You guys are such good friends. Sorry. So good at the friends. I appreciate your effort right there.
All right, so today we're going to start. We mentioned this before. We're going to start talking about our nonlinear linked data structures. So not in a line, and we're going to start talking about binary trees. All right, so a binary tree is a nonlinear linked data structure where nodes to the left of a node are less than or equal to the node's payload, and nodes to the right of a node are greater than the node's payload. All right, so let me give you a visual example. So let's say we're going to have a binary tree of numbers. All right, so let's just say the top of my tree. So the very first node I add to my empty tree is a 5. All right, it's got nowhere to go except top of the tree. All right, so let's say the next thing I'm adding is a 3. What do you want? You want to add 8? That's what you said? What? Did you suggest a number? What's your favorite number?
I don't know.
Pick a number.
I'm real sad right now.
Pick a number. 3. All right. All right. So 3, we're adding this to the tree, so we kind of drop it onto the top of the tree here, and it's gonna end up landing where it's supposed to land. All right. Now from this previous slide, we said that nodes, and actually let me break this up a little bit so maybe it's a little bit easier to read. Nodes to the left of a node are less than or equal to the node's payload. Nodes to the right of the node are greater than the node's payload. So is 3 less than or equal to 5, or is 3 greater than 5? Less than or equal to 5. So we're going to drop it onto the tree. We're going to say, can we add it here? No. Space is occupied. All right. So should this guy go to the left or should he go to the right? He should go to the left. So we're going to drop him to the left. Can we add him here? Yes, we can. It's an available space. So we'll just drop him there to the left. All right. Now, let's add another value. Let's do a 2. Actually, let's do another 3 so we can test the equal to 2. So we drop it onto the top of the tree. Can we place it here? Nope. Space is occupied. Should this guy go to the left or to the right? To the left. Should go to the left. So we come here. Can we put him here? No. Nope. Space is occupied. Should this guy go to the left or to the right?
To the left.
To the left. Can we put him here? Yep, it's an available space, so we'll set his value there.
Hang on, what is the purpose of this?
Purpose of it right now is to know how to add stuff to the tree. Then we'll figure out how to use trees. It's for sorting. Searching and sorting. You can learn, things end up in order, you'll see.
Why do we have different way of sorting?
Well, bird sort was too easy. All right, so now we're going to do an 8. So we drop an 8 onto the top of the tree. Can we place it at the top? Nope.
Nope.
Should an 8 go to the right or left?
To the right.
To the right. Can we place it here? Yep. So we'll go ahead and drop it, and that's his final location. We'll do another one. Let's do a 6. So we drop a 6 in. Can we put him here?
No.
Nope. Should he go left or right?
To the right.
Right. Can we put him here?
No.
Nope. Should he go left or right?
Left.
He should go left because he's less than or equal to 8. So we'll place him here. And if we want to spread this out a little bit just so we can really see the tree being divided.
How come the 3 also goes to the left if it's the same value? Is it just that how it is? Oh, there you go.
Less than or equal to. All right. So does that make sense? How a tree works? Binary tree works? So every child, let's go ahead and add that note. Let's say every node has at most 2 child nodes. Hence binary. 2. Okay? So a child can have a left or a right node, but at most 2. So for instance, this guy right here, he has 2 child nodes. He has a left node and he has a right node. This guy only has 1 child node. He has a left node, but no right node. This guy has only 1 child node. He has a left node and no right node. This guy has 0 children. This guy has 0 children. Nodes with 0 children, and this is more just a vocabulary thing, are known as leaf nodes. Okay, they're called leaf nodes. Yeah, that makes sense?
Is that because they're free?
They're the leaves that they. Well, first of all, let's ask the question: why is this guy called a tree? He actually will end up looking like a tree, but he's like an upside down tree, right? This is the main trunk, the base of the tree where it's planted in the ground, and then everything kind of flows off of that. So anything that doesn't have any branches and stuff coming off of it, those are the leaves of a tree, right? Make sense? All right. So now to answer V's question. Okay. Yes, it was the number you thought you saw.
What's the number I
That's the answer to your other question. You just kept looking at your grade and seeing if the numbers changed. There's always another day. You should come to Bible study today.
No.
That'll make you feel better. Free lunch.
No, I don't want to see him.
So good. I was telling them how you kept checking on me last night. You thought or you're hoping?
No, I thought you were dying.
Well, I had to go to 2 different doctors. The first one, so I walk into this place because I have all this pressure inside my face and I can't see out of my left eye, right?
Mm-hmm.
And I go in, he takes all these, he takes x-rays and stuff. The guy didn't seem very competent at all. Okay, so in the end, he says, oh, I'm pretty sure it's allergies. Tells me to take an over-the-counter allergy pill. Look, which I have environmental allergies. I play golf all the time. So, I already take a daily Zyrtec.
Mm-hmm.
So I'm like, I already take them. So here's another one. This is the one I take. It works. Like, I can't see out of my left eye. Okay, I don't think this is allergies. He's like, well, it's not. We don't need antibiotics. The X-ray looks fine. Or I guess X-rays don't really show anything with sinuses or something. So then I went to a different urgent care for a second opinion, and then within like 5 minutes they're shipping me down to the MRI. It's like, yeah, this isn't allergies. Then they're throwing me on steroids and having me do a CT scan today. So that's what I had this morning. But the steroids seem to have helped the eye quite a bit. It never went dark. I just everything was super blurry out of my left eye. But what was funny is my total vision was better. So I wear glasses, I have contacts in, and my correct vision is like not quite 20/20, like 20/25 or something like that. But my bad eye is my left eye. So my right eye is a clearer eye. Well, with my left eye being even worse yesterday, my right eye was having to work harder. I actually saw 20/16 on my test. It improved my overall vision. So I'm walking in complaining that I'm not seeing well out of my left eye, and they're like, "What are you bitching about? It's an upgrade." The only animal that has better vision now is an eagle, and it's closer than it should be. They're like pointing to like line 4 from the bottom of the thing, and like, can you see this? They're pretty fuzzy. I'm like just rattling off the very bottom line, reading like the manufacturer of the poster.
I didn't know it was on there.
It's like, well, can you see that they're out there with a magnifying glass?
Is your field of view reduced though?
No, it was just this was all blurry.
Really?
Yeah.
Interesting.
So when I was driving to these different clinics, I'm having to drive like this and just do like doing like a street scan.
Oh my God.
But in the end, the CT scan is meant to confirm it. They're pretty sure it's still just the sinus infection, but actually probably the infection's gone. But I've been on drugs and stuff for so long now with 4 different antibiotics and all this other, cold medicine and stuff like that I guess after the infection's gone, you can have all this inflammation that doesn't go away. So this is just inflammation that's pushing on my optic nerve. So I might not even need more medicine. They put me on the steroid last night, which is supposed to bring inflammation down really quickly, and then it might just be like, you're good. And I met my deductible because those machines looked expensive. I spent a total of maybe a minute and a half in these machines, and it's probably gonna be like a $14,000 bill. All right, so let's talk about tree traversal here for V. So we have 3 different ways of traversing a tree. Okay, we have in order, pre-order, post-order. All right, so let's spell it out in words first, and then we'll see an example of these. So in order, all this is relative to an individual node. All right, so in order says visit the left node. Well, let's see, visit left node. Do I want to say even visit in there? Yeah. Visit left, visit yourself, visit right. That's in order. Pre-order is visit yourself, visit left, visit right. Post-order is visit left, visit right, visit yourself. So this is all relative to the node. If I'm a node, this is all relative to when do I look at me. If it's in order, I check the left, I check myself, I check the right. If it's pre-order, I check myself, I check the left, I check the right. If it's post-order, I check the left, I check the right, then I finally, afterwards, check myself. Make sense? Now, how many of you think this is an important concept? I will tell you, at least this year, this was a question on the 490 competency exam. Senior seminar, the big exam that you have to pass in order to graduate. Yeah. All right, so important concept. All right. Now, you're going to see, because I mentioned a little bit ago, that one of these has to do with sorting. The other two actually have to do with the performance related to searching. Okay, and we're not actually going to focus too much on that in here. That's more of like a database topic. Databases are often implemented in terms of trees. All right, but you'll at least be able to see kind of the idea of it. So let's go ahead and underneath each of these, let's put our order from this guy. All right, so in order says we're visiting left, then we're going to visit ourselves, then we're going to visit right. Now, this is kind of a lesson on recursion. All right, because you're going to see how this works. You might say, well, if I'm visiting left, then myself, then the right, the first three numbers would be 3, 5, 8. But it's not. Remember, this is all relative to an individual node. Every node we go to, we're visiting in order. So in order says, I'm going to visit this in order. So the first thing I'm going to do is I'm going to visit left. Now I need to visit this guy in order. So what's the first thing I do? I visit left. I need to visit this guy in order. So what's the first thing I do? I try to visit left. There's nothing to the left. Then I visit myself. Okay, so my first value I get here is a 3. Okay. Then I try to visit the right. Nothing there. So now I've completed visiting this node in order. I bounce back up. I visit myself. Then I visit the right. Nothing there. Bounce back up because I've completed visiting this guy in order. Now I visit myself. This is a 5. Then I visit the right. Now I visit this guy in order. So I visit the left. Now I visit this guy in order. I try to visit the left. Then I visit myself. So there's a 6. Then I visit myself. Well, actually, I'm sorry. So I tried to visit left. Nothing there. Visited myself. Tried to visit right. Nothing there. Now I'm done visiting this node. Bounce back up. I visit myself here. So that's my 8. Then he goes to visit the right, nothing there. So we're done visiting this node in order. Bounce back up, we're done visiting this node in order. So we're done. And notice that I have a 3, 3, 5, 6, 8. They're in sorted order. Right? So if we have data and we add that data to a binary tree, we're adding it in such a way that it's a kind of efficient, it's stored in such a way that it can be easily pulled out in a sorted way. That makes sense? By choosing to visit these nodes in order. Got it? All right, so this is our in order example. I'll throw that underneath here. I just told you for sorting. So let's look.
What is a good example that?
Yeah, here's the good example. Let's say you have since I've been spending some time in doctors' offices, let's say you have 10,000 patient records, and you have these things all stored inside of an array. Now, chances are you're going to just be adding those records, or maybe it's a linked list because you don't know how many patients you're going to have. As new patients get put into the system, you're adding them just to the end of the linked list, right? So your list is not actually sorted, okay? Unless you lucked out and your patients just happen to visit your clinic in alphabetical order, right? Okay, so you have this big long list of patients. Now, when you go to run reports, you want to do a search on those patients. You want to find Mike Littman. You know, you're going to go and look at the L's, right? But that presumes that this list is in order. Because if that list is not in order, the L's could be at the beginning, the L's could be at the end, they could be anywhere in there. So your option is to do a sequential search, which means you start at bucket 0. Is this Mike Lippman? Nope. Is this Mike Lippman? Nope. Is this Mike Lippman? And if you have 10,000 patients, you might have to check 10,000 times. Make sense? So then what can we do? We can apply one of our sorting algorithms to this. We can do an insertion sort. We can do a merge sort because that's fun, right? And then we can get that guy sorted in telephone book order. So then we can just go to the L's and find Mike Lippman more quickly, right? Just a couple of jumps, we'll find, you kind of, as a human being, we just kind of zip down to the L's and kind of glance around in that area and like, there's Mike Lippman, right? Really, what we're doing is something called a binary search, where we're going to the middle, then we're saying which half of the telephone book is he in. We go to that half, we go to the middle of that, and then we finally, after 4 or 5 steps, narrow down to the one guy, right? So now, so it's easier to search for a piece of information inside of data that's sorted. But sorting data can be expensive, especially if we have to do it often, right? So if we have this linked list of sorted, let's say we sort it once. We have 10,000 patients. Now our 10,001st patient walks in, and we need to add him to this list. Well, we can do a couple things. Probably the programmatic convenient thing would be to add them to the end of the list and resort the list. Just who cares how much time it takes, right? But we could go through and say, okay, well, where in here does Mike Lippman belong? So we'll add an index, pop it in there. So we can do that, but now we're gonna have to write the algorithm to go and figure out where this guy lives in our collection, right? Well, what if instead of using a linked list, we used a binary tree as our collection? Every single time a new patient comes in, all we have to do is add the patient to the binary tree. And he automatically plinks down into the right bucket such that when we need our patients in order, we can ask the binary tree, give me the in-order version of yourself, which is the sorted version of yourself. And then we can go and find that patient very quickly. So it's a convenience from a performance perspective of storing your data such that it is always in a already sorted format. That makes sense? Which then allows us to search it more efficiently. All right. So it kind of looks really weird, doesn't it? It seems like it'd just be better to just do this. All right, so that is in order. Now, pre-order, we're pretty much going to go through the same process, except we always visit ourself first. All right, so I'll go ahead and here, we'll just label this in order and leave it on the slide. All right, so now we're doing, let's say pre-order. All right, pre-order says we visit ourselves, then we visit the left, then we visit the right. All right, so pre-order, we come into our tree, we visit ourselves. 5. Next thing I do is I visit the guy to the left. Okay, so I'm going to visit this guy pre-order. What's the first thing I do? I visit myself. Then next thing I do is I visit the guy to the left. First thing I do is I visit myself. Then I visit the left, nothing to the left. Then I visit the right, nothing to the right. I'm done doing pre-order in this guy. Bounce back up, visit the guy on the right, nothing there. I'm done doing pre-order in this guy. Bounce back up, visit the right. What's the first thing I do? Visit myself, that's the 8. Then I check the left. What's the first thing I do? Visit myself, there's the 6. Then I check the left, nothing there. Then I check the right, nothing there. We're done visiting this guy pre-order. Bounce back up, we check the right, nothing there. Done visiting this guy pre-order. Bounce back up, done visiting this guy pre-order. There's our list order for pre-order. Okay, what this guy is called. So notice the numbers here. So we started at the top of our list. So let's assume, and this is really something that's applied more to a something called an n-ary tree instead of a binary tree. Binary trees have the convenience of being stored in a sorted order, where, and that's because we know everything to the left is less than or equal to, everything to the right is greater than.
Mhm.
That's the rule of a binary tree. That's what makes a binary tree a binary tree. Okay, that there's at most 2 children, and we know a lot about each of the children based on the parent. Okay, what their value is. Now, if we had other kinds of trees, like an n-ary tree, where every node can have 0 or more children, we can choose to visit things in other orders, like a pre-order, and that would allow us to find things higher up in the tree. Right? So let's assume that the data we were searching for happened to be higher here, and it's as opposed to way down the tree all the way on this side, something like that. We can choose to do a pre-order, which would then allow us to search through unsorted data potentially more quickly, if the data we were looking for happened to be near the top. Make sense? Similarly, with a post order, it would allow us to find stuff that's near the bottom more quickly if it happened to be near the bottom. Well, I can't really give you, that's where I said we're going to throw it over to the database class, because that's one of the things we do with n-ary trees is we do something called tree balancing, where you always make sure that your tree is not too deep. So we keep rotating the tree such that, what you don't want to have is you don't want to have this situation where you have, node after node after node just kind of hanging off one side of the tree. So you got you're out in the forest, you see one of these really freak show trees that has like no leaves or branches on one side and just everything on the left. Okay, and even worse in this case where it's like just one line of branches that come down with leaves hanging off of it, and nothing else over there. If we were doing a pre-order traversal of this, searching for a value, we'd have to get pretty lucky, because a majority of the nodes on this tree, and you can see if I take this to a longer example, are deep in the tree. So we'd have to check. Each time we check a node, it's an if statement. Is this what we're looking for? Is this what we're looking for? Is this what we're looking for? So on and so forth. So if we're talking about efficiency of searching for data, we want to have our data set up in such a way that we have to ask the fewest number of questions. Mm-hmm. All right. So tree data structures tend to be at the heart of modern day. Well, modern day is maybe a little bit less. Well, it's still true. Let's call it instead of, I'll just take the modern day thing off the front of it. Tends to be at the heart of database design. The way we store data in a traversable way. A way that we can walk through the data and say, is this what I'm looking for? Is this what I'm looking for? Is this what I'm looking for? Okay. Based on what we've done up to this point, in our context, a binary tree is going to be, a lot of times they're called binary search trees. Okay, so it allows us to search for data, and we've decided that searching for data, just like we do in normal life, tends to be easier when we have data that is in a recognizable order. That makes sense? So at the end of the day, without a database example, I can't give you necessarily a great example of pre or post order, because it has to do with searching efficiency in data isn't necessarily sorted. When you think about databases, you don't necessarily have just this giant collection of patient records. You have a bunch of data here that means one thing. You have a bunch of data here that means something else. You have a bunch of data here that means something else. Some of this data is related to each other loosely. Some of this data has nothing to do with each other. Like for the hackathon, you were creating authentication tables. So, you might have had stuff in your Firebase that kind of had profile information associated with a unique user ID. Everything in that database is related to user ID. So for that one table, for that one data structure, it was probably being represented as some sort of tree structure behind the scenes. All right. But if you have multiple tree structures, having them individually sorted doesn't really help you. Does that make sense? So if I go into the hospital, their list of patient records has nothing to do with their current list of medical supplies. Right? Those are two completely separate collections. Yet at some point in there, they're going to have to say, okay, patient X is having procedure Y, which needs these 4 medical supplies. So you're having to do searches on one collection of data that's sort of unrelated to this other collection of data, other than stuff's leaving this collection because we just took 12 pieces of gauze or whatever it is, that kind of stuff. Right? So it applies to different kinds of problems. In our world right now, we're looking at the underlying data structure, which is a tree-based data structure, and we're saying what makes sense in our world right now is we typically will search through collections of data. It's typically easier for us to search through a collection of data if it's sorted. That's a human way of looking at things. I know you don't use telephone books anymore, but when we did use telephone books, you relied on the fact that they were in alphabetical order. Okay? If you use a dictionary, you rely on the fact that it's in alphabetical order. Wouldn't it be a lot more difficult to find a word in the dictionary if it wasn't in alphabetical order? Start the hunt. Well, probably not with Google, it wouldn't be. No, I would use the same term. If I want to find out the definition of a word, I just say, define the name of the word, and Google does the rest. I don't care how it's finding it. If he wants to waste his precious microseconds on doing a sequential search of all the languages in human history, I'll wait a quarter of a second. I'm cool with that. But from a human version of problem solving, we like sorted stuff, right? And you can maybe even take it down to a more practical level, like if you're playing with a deck of cards. Once you've shuffled those cards and somebody says, find the 5 of diamonds, you got to flip through the whole deck until you finally come upon the 5 of diamonds, because it's no longer in a known order, right? And when you first open that deck of cards, they're typically in order. You have all the 2s next to each other, all the 3s next to each other. So you just kind of flip to where the 5s are and pull out the one with the right suit. And now you have it. So it was a kind of a sorted situation, and humans are very compatible with that. All right. So let's do our our post order, and then we're going to rate this. Now, just a quick question. Do you kind of see where I'm talking about that this, let's see, I had 2 3s, correct? These are the new ones I added? Okay. Do you kind of see what I'm saying when I said this kind of relates to recursion? Each time I jump to a node, I started over with this idea of pre or post or in order, right? Because that's a call to that function. I am performing the post order function on this guy right here. And post order function on that guy says visit the left, then visit the right, then visit yourself. Last. That's what post order says. So in order to visit the post order of, go ahead.
So this call recursion?
It would be. Yeah, you're gonna see how it's gonna work. But yeah. So to visit this guy in a post order way, my rule is I first visit his left child. Then I visit his right child. And then I visit myself. But before I can visit the right child, I have to fully visit the left child, which means I'm saying I'm going to visit the left child in post order. I still haven't collected any numbers yet, right? Because when I'm at this guy, I'm making a recursive call to post order on this node. And when I call post order on a node, what do? I check the left, then I check the right, then I check myself. Well, in this case, I'm going to call post order on the left. Then I call post order on his left. Nothing to do, bounces back. Then I call post order on his right. Nothing to do, bounces back. Then I finish up this call to post order, and I get a 3. Now I'm done with that call to post order. I bounce back up to this call to post order where I've just finished my first call to the left side. Kind of like merge sort, right? Sort the left, sort the right. So now I've just finished my first call to post order here. So now I make my second call to search the right. Nothing there. Bounce back, visit myself. Oh. Now I'm done with this call to post order. Bounce back up. He's finished with his first recursive call to post order where he checked his left child. So now he's going to call post order on his right child. Who's going to call post order on his left child? Who's going to call post order on his left child? Nothing to do. Who's going to call post order on his right child? Nothing to do. Who's finally going to visit himself? Notice how this is getting the bottom of the tree first? Or if we flip the tree over, it's the top of the tree first. This is a depth, kind of a depth first search, sort of. All right, so I just visited this guy, so now I'm done with this call to post order. Bounce back up. I make a call to post order for my right child. Nothing to do. Bounce back up. Visit myself. Now I finished this call to post order. Bounce back up. So now this guy has had his second call to post order return. He checked his left children, had it do its whole rigmarole. Had his right children do their whole rigmarole. Now he's finally, at the end, going to visit himself. And there's my post order.
So for pre and post order, the way you can tell the difference is if you have your starting number either in the front or back. Is that kind of a good key to remember?
I would say at this point, I wouldn't necessarily really try to think about their uses yet.
Okay.
Just think about how you visit, the order in which you visit. So, because really what we're talking about here at the top level here is, where did I write it? Tree traversal. What are the various ways I can visit the nodes of a tree? Yeah. Where the one that we can see right now that certainly has a practical value is in order, right? I promise you there are practical values for these other ones, but it's when they're applied to other kinds of problems, where it's real easy for us to conceive of searching through data as a problem. You know, we do it. We look in the dictionary, whatever, and if I can conveniently just drop stuff into a tree and it kind of drops down to where it's supposed to live, no matter what order I put the stuff in there, and then I can quickly gather it in order, that's great. That's a quick sort, because the data was already created in such a way, was stored in such a way that it was immediately convertible to a sorted format. Make sense? Rather than a linked list, which might just be a hodgepodge of data and you make no assumptions about what order that stuff is in. You can't take any shortcuts. In this case, because of how we stored our data, because of the rules we've applied to the binary tree, we now know that we can make some assumptions of our data as we're putting it back together. And if we visit it in a very specific way, we have sorted data. That makes sense? All right, so let's write some of this. So what I want to do is we're going to create a, what's up?
Question. So is it the non-linear one is more efficient than the linear one?
Depends what you're using it for. It's always the right tool for the job. So if you're just storing a collection of random stuff that never needs to be sorted or something like that, a linear linked list is a less complicated data structure. Might as well throw it in that. Linear linked lists are kind of like our memory efficient version of arrays. But if you need to have data that is held in a efficient format, such that we can easily search it or more easily search it, binary trees make a lot of sense. Now, take that to the next step. We're not talking about it yet, but we can pretty quickly. I mean, I mentioned n-array trees today, right? Mm-hmm. Which kind of remove that rule of only at most 2 children. Now they're going to have however many children you want. And at that point, we're taking away a lot of that preconceived, a lot of those assumptions. Now we just have a collection of stuff, right? But you might say, well, when would you do that? Well, what if you're creating, so this is more of a video game example. What if you're creating like a map of a dungeon? You're in a room and you can go north, south, east, west. That's 4 child nodes. Oh. And then you're in that room and maybe let's say you have north, south, east, west, up, down. Now you have 6 child nodes. And you're in another room and you can only go north, 1 child node. So you can actually create a map of stuff using a n-array linked list or an n-array tree. Now, what if you have rooms that circle back on each other? Now that just became something called a graph, the next level. Right. So that's our real world maps, right? How many of you have ever been to Cedarburg? Is there only one way to get to Cedarburg? You can get to Cedarburg through multiple roads, right? Okay. So if you were to, think about the map of Wisconsin or the map of Ozaki County or something like that in terms of a graph, each town is a node, and then you have edges that go between those nodes, right? And I can get to Cedarburg from here by taking, I guess I could take Highland up, and then, so I could take that up to, let's just call it, there's probably some municipality up there, and then I turn right and hit Cedarburg. Let's just keep it simple. All right. So I can traverse my graph in that way, but then I can actually come all the way back to Mequon, taking completely other edges, other roads, right? I can kind of circle up through Grafton, and then, heck, if I want to be really inefficient about this, I can go up to Port and kind of come back down by the lake, ultimately get back down to Mequon. So I've made a cycle. I've circled through it. I have multiple edges and all. So now you have a single node, like Mequon, that actually has more than one parent. This node has a single parent. This node has a single parent. In n-ary trees, every node has a single parent. Just a parent could have more than 2 children. In a graph, anything goes, which then makes it appropriate for a lot of real life examples, right? Like maps are something that are pretty common to us, right? So what I just told you is, how does Google Maps work under the hood? Google Maps is storing that map data as a graph, and it's solving a problem that's actually a really common, famous problem that I'm sure you'll talk about in detail in 490. Have you heard about the TSP? Ever seen that in a textbook or something? How many L's in traveling? 5? Heard of the traveling salesman problem before?
Yeah.
Okay, it's a kind of a famous computer science problem, so sometimes just called TSP. So traveling salesman problem, not a hard concept to wrap your mind around. You're a salesman, and pick the product you're selling Bibles, okay? And you have to visit 10 cities in a certain day. And you want to be as fuel efficient as possible on your gas bill. So what's the most efficient way of visiting those 10 cities, returning back to your home base that day? What city do you go to first, then second, then third? Does that make sense? So if you were to, and I promise you, under the hood, how many of you have ever used Google Maps and or any mapping software, but let's just use Google Maps as an example, and did the add stop thing? You put in your final destination, and then you add stops in between. So if you have 10 cities to visit, and you put your final destination to home, which is where you're starting, it's going to say, well, you're here, dude. Okay. But then you start adding stops, and you add Cedarburg, and you add Germantown, and you add Port Washington. It will ultimately, now the default is it'll visit them in the order you put them in. Okay. But I think there's a setting, I might be lying. There at least used to be a setting that said, I want to visit all these places, create my itinerary, something like that. But that would use a traveling salesman problem, where it says, tell me the order I should drive to get to all these places today, disregarding the order in which I want to visit them. And that's actually a time complexity, computationally expensive problem to solve. But the underlying data structure for that is a graph. Why? Because that's the correct data structure for the job. That's how we can represent what we view as a street map. You got 20 different roads that come to Mequon. And that means Mequon, from a graph perspective, has 20 different parents. Right? It's a little kludgy when you get to the family tree side of things. But it's kind of like throwing darts with hand grenades, right? All right, so this is kind of like the big picture of these non-linear linked data structures. All right, so we're dealing with the most simplistic one, really, at this point: binary trees. Every node has at most one parent. Every parent has at most 2 children. Easy peasy. All right, makes sense? So what we want to do here is I'm going to start a new Android Studio project. And I'll make this an empty activity. And we're going to call this guy CSC300 binary tree, something like that. Oh, thought I heard my phone buzzing. CSC300 binary tree, and yeah, all that rest is fine. What's with the little happy and sad faces down here?
Maybe it's for your experience.
Click to let Google know that you are unhappy with your experience.
There's a doctor right next to it.
No, this is a doctor? That is a doctor. You have better vision than me, but that's not surprising. Yeah, but which is to get the small up close font. I have eagle vision with my contacts from a distance. I've lost all sorts of close stuff. All right. So that's what I tell people. So I used to wear trifocals, so I could see tiny, tiny font on computer screens pretty easily. Now I can like barely see what's on this computer screen because this vision is like my worst vision now. But it's helped me a lot for golf because I can see super distance now, where I used to basically lose the ball when I hit it because it would cross the focals and it's gone. And now, I mean, I can see the thing bounce out, and I can wear the cool kid sunglasses. So good. All right, so I'm going to create a couple of classes. So one of them is going to be our common one that we've seen before. We're going to call this a node. So let's go into our keynote here, and let's design these guys. We've decided that in a binary tree, a node has a payload, and it has a maximum of 2 children. Right? Mm-hmm. All right, so we're going to have a payload. We're going to have a node, left node. We're going to have a node, right node.
Hang on. Why do we only have 2 children?
Maximum of 2 children, because that's this guy right here.
Like, what if we have, more than 2?
You can't have more than 2 in a binary tree. Binary trees have a maximum of 2 children. Yep, so this guy has 2 kids. This guy has 1 kid. This guy has 0 kids. What do we call nodes with 0 kids?
A leaf.
A leaf. This guy has 1 kid, 0 kids, 2 kids. Makes sense? So maximum of 2 kids. 2 children. All right, so for our node here, pretty common thing that we've done before, we're going to be creating a binary tree of integers, but you can have a binary tree of patient records if you want, where everything to the left is less than or equal to the parent node. So you have to decide, what does it mean for a patient record to be less than another patient record? Maybe it's date since they joined the practice, since they became a patient. Maybe it's age. Maybe it's alphabetical. Alphabetical probably makes the most sense based on last name. That's kind of the way we usually think about people's names, right? Okay, but you can decide what that means. But for us, we're going to do just numbers first. All right. So, actually, yeah, we'll do numbers first. I'll leave the patient record thing for an assignment. It'll be a good one. But not until after Easter.
Okay, that's Tiger 1.
Tiger 1. So I promised assignment for Thursday, right?
Really?
Did you even know Tiger 1?
He did it again.
Hey, that 8-ball thing said it was right.
True. It did. It did.
Probably.
It's like historic. They're awarding him the Medal of Freedom. True. You hear that? He's getting the Congressional Medal of Freedom.
What's that for?
Most likely.
The president gives you it's the highest civilian honor you can get in the country. It's like a medal, for doing great things, or
Interesting.
Huh? Yeah, I think it's kind of like being knighted for the United States, since we don't have a monarchy.
That's kind of cool, but like, got it because you played golf really well.
A lot of athletes have gotten it for
Really?
but I mean, if you knew the whole this was really
Okay.
pretty
I
special.
don't know the backstory super detailed.
Yeah.
But I mean, you gave me.
Short version of this guy couldn't get out of a chair a year and a half ago.
Oh.
He couldn't pick his kids up from school. So,
Tiger Woods?
yeah.
Why, did he just break his back or something?
He had 6 back surgeries, and his most recent one was a fusion, which says you basically are never coming back to a sport that requires torquing on your lower back.
And yet
he just won the Masters.
Wow.
And before that, he had reconstructive surgery on both knees. And somewhere in the middle, he got into some domestic issues with some waitresses and porn stars, I think. And infidelity was not his, fidelity was not a strong point for him. But he's my favorite golfer. I wouldn't give him husband of the year or anything like that. 2 completely separate things. What do they say? Never meet your heroes? They say something along those lines because they'll always disappoint you.
Hope Solo.
What's this?
Hope Solo.
Yeah.
The U.S. women's team.
Oh, yeah.
That was rough.
Okay, so a node, we're going to have a private int payload. We should start looking pretty familiar, right? Every time we're creating nodes, we're holding the payload. It's just kind of that's what linked data structures is, kind of the stock thing. Linked data structures are nodes that are linked together, and nodes hold a payload, a value. In this case, the type of value we're holding are integers. All right, so then we're going to have a private node left child, private node right child. Then we'll have our constructor, public node. This guy will take in an int payload. So when a node first comes into existence, he will have a value, will have a payload, but he has no children. So we'll say this dot payload is equal to payload. This dot left child is equal to null. This dot right child is equal to null. Make sense? All right, then we need to go ahead and get our getter for payload and our setters and getters for the children. So I'll right click, generate. We'll go ahead and give ourselves a getter for payload. We won't allow us to change our payload, but we can retrieve our payload if we want it. And then we'll give ourselves a getter and setter for our left child and our right child. So that's our node class. Okay. Little bit more involved than our link list and stack nodes, but ballparky similar things, right? This is where we get nonlinear. A link list and a stack and a queue at most have one child, one neighbor, right? So we don't think of it as a tree because it's a line, because they only link to one other thing, which links to one other thing, which links to one other thing. It's a linear linked data structure. Now we have something that potentially can link to 2 other things, i.e. nonlinear linked data structure. Get it? All right, so now we're going to create our binary tree class. Okay. And our binary tree, we're going to have a top of the tree or a root node of the tree. Okay, so we'll have a private node root. We'll have our public binary tree. We'll take in no parameters. And an empty binary tree is something we've, I guess, just planted, and there's currently nothing growing out of the ground. So that would be this dot root is equal to null. That's an empty tree, right? Then we have a public void add. So we'll add an integer to our binary tree. Now, what we do is we're going to add this guy to our tree. And we've already seen how adding to trees work. The first thing we do is we say, if it's the empty tree, I can just add it right here to the top, right? All right, so what we can actually do here is we can go ahead and build a node out of this guy. So I'll say node n is equal to a new node passing it the payload. So now I have an actual node. that has a payload and no children. Okay? I have an object in my hand. I'm putting him somewhere in my tree. Make sense?
Mm-hmm.
All right, so I'm going to ask the question, if this dot root is equal to null, I have found a home, right? So I'll say this dot root is equal to n. And I'm done. Otherwise, if root is not vacant, that means I got to put him somewhere else. So I got to decide where I need to put him, and that's where I have to apply my binary tree rules. So I have to ask about this guy's payload relative to root's payload. And if it's less than or equal to root's payload, I'm going to add him to root's child. Root's left child. If it's greater than root's payload, I'm going to add him to root's right child. Make sense? So we'll ask the question, if n.getPayload, even though we can just call it payload right now because we still have that variable, if that guy is less than or equal to this dot root, which we know is a thing now. If I'm in this else, this dot root's a real thing. Dot get payload. Add to the left. So if n.getPayload is less than or equal to root payload, we're going to be trying to add this guy to the left. Otherwise, he must be greater than root's payload, so we'll be add to the right. Make sense? All right. So what does it mean to add to the left? Well, if root doesn't have a left child, we can just put him there.
Yeah.
Here's your left. Congratulations, it's a boy. Or it's a 7. Okay, something like that. So we'll say if this dot root dot get left child, if that guy is equal to a null, that is the left child of that root does not have a left child, that means he has a vacancy. Therefore, I can say this dot root dot set left child to n. That make sense? Mm-hmm. Similarly, in the add to right thing, if this dot root dot get right child is equal to null, he does not have a right child, then I'll say this dot root dot set right child equal to n. We have vacancies. Otherwise, if we had a left child or we had a right child, and that's where we're supposed to add it, we have to pass the buck. We're going to look down and say, child, here's a node. I'd like you to find him a home. Then it's his job. So that's kind of a recursive call, right? Even though it's technically a different node. At this level, we're at the top level of the binary tree, but you'll see the recursive nature once we get into the nodes. So now, a node itself has to have a way of adding a child. So public void add child. This guy will take in a node n as a parameter. And he's going to ask the question. If this guy exists, if I'm a node, I know he's not taking my place. Okay? The only reason he was passed down to me is because there was not a vacancy on my throne. Okay? So they're handing me this guy and say, find a home for him. So I need to decide, does he go to my left or does he go to my right? If n.getPayload is less than or equal to this dot payload. So if it's less than or equal to my value, then I'm going to add him to my left. If this dot left child is equal to null, I have a vacancy, I can go ahead and say this dot left child is equal to n. Right?
Mm-hmm.
If I don't have a left child, you just became my left child. If I do have a left child, and this is where it's like the pseudo recursion thing. Actually, what I'm going to do is I'm going to write it the more direct way, and then I'm going to show you maybe a little bit better way of writing it. So we're going to say else if he's supposed to go to the left, and I don't have a vacancy to my left. I'm going to pass the buck to the left guy. So this dot left child dot add child n. So that's kind of like my recursive call, where it's a function that calls itself from within itself. But in this case, he's actually calling a duplicate of itself. That is this function with the same name that's actually owned by a different node. So else we'll add it to our left child. Actually, this will make more sense than the other way I was going to show you. So this is better anyways. So else, if I'm not adding it to the left, I should be adding it to the right. So if this dot right child is equal to null, this dot right child is equal to n. Else, this dot right child dot add child n. That's it. So this is like a pseudo recursive call, right? So add child is owned by node. An individual node is going to be trying to add a node somewhere in his tree. Now, he can look to the left or right and say, do I have a vacancy? If I do, I'll place you. But first he has to decide, where in my tree do I live? Okay, should this guy go? So he's going to look at the node he's trying to place. What's my payload? If that's less than or equal to myself, my value, then I know he's going to my left. Is this an immediate child, or is this a pass the buck to the next guy down the road? If I have a vacancy, we'll go ahead and place him. If I don't, it's my left child's problem. Make sense? Otherwise, he's going to live to my right. If I have a vacancy, I'll just place him. Otherwise, it's my right child's problem. We're just passing the buck. So this is pseudo recursion because we are calling the same function, this add child function that we're in the middle of writing right now. It just happens to be owned by a different instance of node, our left or our right child. Make sense? All right, so now that's all of what node is. We'll have to figure out how we're going to display these guys. Okay, but right now we should be able to just add nodes, or add integers in this case, to our binary tree left and right, and trust, obviously without checking, right? Trust that that stuff's going to plink its way down into the tree in the correct place. Now let me ask you this. Does the order in which we add values to a tree matter? If I added these exact same values, so we have 5, 3, 3, 8, 6, whatever. If I added them in a different order, would I have a different tree?
No.
You think it'd be the same tree?
Yeah.
Okay, tell me why you're wrong.
No.
You don't think it's going to be the same tree, even though I just confirmed that it's not the same tree. Go ahead, Luke. Why is it not the same tree?
Because like
Or why did you think it would be the same tree? Let's go that route.
Because in the way that you insert it kind of looks like it's kind of self-sorting. It seems like it'd be inserted in the same way because you're going to the left if it's less than the
So we're gonna
and then it goes to the right.
we'll drag all our Legos over here to the side. Okay, so we'll drag all our Legos over to the side, and here we'll start off right from the beginning. Let's just say we added a 3 first.
Oh, I thought you meant to be okay.
Yeah. If I add these nodes to my tree in a different order,
I thought you
Right.
meant to be started with.
well, fine, we can start with a 5, but it's somewhere in there. I'm going to drop them in a different order.
Mhm.
It doesn't matter which one you start with. So I mean, we can start with a 5, and he'll get added to the root node of your tree. Everything looks legit, right? But the second we say, he mentioned, let's add a 6. Now we're going to add a 6. So this is, what was it, Price is Right, or Let's Make a Deal, where they had the Plinko game. You kind of drop the coin at the top, and it kind of starts bouncing down until it finally goes into one of the buckets. Okay, so we drop this guy into the top of the tree, and we don't have room for him here. Is he less than or equal to 5?
No.
Nope, he's greater than 5. So where are we putting him?
To the right.
To the right. So we checked with this guy's right child. He has a vacancy, so we drop him. Then we can add what do you want to add next? An 8? Okay, so we'll drop the 8 in. No vacancy here. Should you go right or left? To right. No vacancy here. So when we had no vacancy here, so we tried to add him to this node. Can't add him directly. Where should he go? He should go to the right. So he checked his right child to see if he had a right child. Here's the code for that. Do I have a right child? If I don't, go ahead and place him. But in this case, he does have a right child. I can't place him. So what do? I ask that right child to find a home for this guy. That's this line. Right child, go ahead and add this node that I'm passing around. So we pass it to him. He looks at it and says, should this guy go to my left or should it go to my right? Go to my right. So he checks, do I have a right child? That's this code right here. Do I have a right child? I don't. So since my right child is equal to null, I can go ahead and place the value. And that's where its final home is. So right off the bat here, Luke, you see we have a different tree.
Yeah.
Right? So we can keep adding this stuff, but that's actually an important thing when you move forward with nonlinear data structures, is it does matter the order you add stuff to your tree. So, and that's where we get, and we'll talk about this probably after Easter, but we get this idea of an unbalanced tree. And when you get an unbalanced tree, we kind of saw the example a little bit ago where I said we created the freak tree that had all the branches going off to one side. It was like really left heavy and had like nothing on the right, something like that. Now, that's okay. It still will work algorithmically if you're doing searches and things like that, but it's likely to be a lot less efficient on average. You might luck out. Might be the first thing you're looking for and first thing you find, and life goes on. But ideally, you want to give an average search time for things that is, that you can rely on. So you want to have trees that look, it's when you go outside, you see that beautiful tree that's just really symmetrical. I don't see them as beautiful, but whatever. Okay, but you have these trees that are very, very symmetrical, and that would be the easiest tree, or the on average best search time. There might be times that it would be faster with a lopsided tree because your value is higher up, but most of the time probably not most, on average, your search time will be dependable, something along those lines, right? So we'll actually look at AVL trees, which are self-balancing trees, where every single time we add something, we sit there and we kind of give a little chiropractic adjustment to the tree. We look at it and say, is this thing a little lopsided? Is the left side a little bit too heavy? And if it is, what we'll actually do is we'll shift the tree, which might give us a new parent node. Might give us a new root node at the top. Does that make sense? Sometimes we'll have to shift it up to that level. Sometimes it'll just be an inner shift where we just take, like the shoulder joint or something and give it a little tweak. Okay, but the whole idea is, and why it makes sense to do that every single time we add a value, is because we can center in on where we just knocked the tree out of balance. We know if our tree is out of balance now, we can ask the question, is the depth on the left greater than the depth on the right by more than one? Say, we'll talk about this in detail when we look at that. Then we can say, we're going to go ahead and we're going to adjust this tree to get it back into balance to make sure it's efficient to search, something like that. And that becomes a fairly hard problem. That's a complex problem. It's expensive to keep a tree balanced, but it's kind of is the juice worth the squeeze? If you have lots of data that you're often searching, it may be very valuable to you to keep that tree very balanced, because you're going to make up any time you're spending right now in the long run if you're searching this data often.
Kind of like what you were saying before with how the dictionary would be out of order. It'd be hard to find stuff.
Well, yeah, but that has more to do with how you choose to use the tree. That's with the traversal stuff. I don't care how lopsided your binary tree is. If you visit it in order, you're going to have an ordered list. Okay? It doesn't matter how bad it is. The rules of a binary tree protect against that.
So,
You just might be doing a really deep traversal on one side and, very superficial on the other side. It's a real shallow pond over there or something like that. So does that make some sense? All right, so what we have here in our current implementation is we have a working node for our binary tree. We didn't test it, but trust me, it's working. And we're going to turn this into an Android app next time, where we'll actually be able to walk our tree ourselves. So we'll have, this is the current screen, here's our payload, here's the potential 2 children. Buttons will show up whether there's a child that exists or not. We click a button, it traverses our tree. So we'll be able to walk through our tree and see it work. And then we'll have buttons for in-order and post-order and pre-order, and you guys will have to implement those things and that kind of stuff. Make sense? Okay. So remember today, student, faculty, staff, Bible study, God and Garub. Just go to the cafeteria, sign in, get a tray, take it down to the terrace room. Keep an eye on Slack regarding Thursday in case I have strange appointments or something like that. But in any case, I will see you then.
We have Easter open house too at 2.
Easter over when is it?
Easter open house.
When?
2 p.m.
Today.
Yes.
And what's at Easter open house?
There's food, there's egg dyeing, there's whatever. Cake walk.
Is there good food?
Yeah.
What kind of food?
I don't know.
You don't know what the good food is.
My goodness.
It's the good food.
It's
You
just
didn't
a
have to
good
say it.
food.
It's the good food.
It's a question mark mystery.